Thank you for the introduction. My name is Sangxia Huang, and I'm a researcher from Sony's Research Center in Lund, in Sweden. So this is where we're located, and we are part of Sony's many research labs around the world. And our research focus in Lund is primarily in 5G and also in IoT. And in the IoT area, we look into technologies that have applications in sort of many different scenarios. So things like edge compute, but also security and privacy and so on. And for this talk, I think it would be more fun to just show a very concrete application. So this is the gym we have in the basement of our office building. And we were just thinking, well, wouldn't it be nice if we can have a system that can keep track of all the exercise we do and provide some feedback for each individual. So if you think about it, if you're doing exercise on the machine, that's kind of an easy problem to solve. And some of the newer and smarter machines already reports these kind of things. But if you're lifting a dumbbell, that's a bit more difficult. And we felt that, well, it's sort of natural to just put up a camera and do something with video. So what exactly do we need to do here? Well, first we have to be able to keep track of each exerciser because we want to provide some personalized feedback. And then we also need to recognize different kinds of exercises and also count how many, that sort of thing. So what's exactly difficult here? It is a crowded environment, although in this picture there's nobody. And then there are, sometimes the lighting condition is not very good. There's usually a big mirror in the gym, and that can cause problem. And also, we want to develop some algorithm that can, let's say we collect video in our basement, and then we install it in a new gym. And hopefully that would also work in a new environment. But if you look at sort of standard benchmark tasks on object detection or tracking or activity recognition, they can do a lot of useful stuff, but if we want to do these kind of real-time and also feedback for each individual, they don't seem to be robust enough. So you can keep track of a person for 20 seconds, 5 minutes, but then you lose track. But of course, we don't have to just rely on one camera. We can put up a lot of them and hope to get some redundancy that way. And that is exactly what we did. So you're seeing a demo of just keeping track of people on multiple camera. So we set up a few cameras and we did some calibration. So just we know where the cameras are and which way they are pointing at. And then on each single video stream, we just run some pre-trained people detection or body key point detection model. And then using our knowledge about the geometry, so where the cameras are, we started to look at how to combine these metadata stream from each individual video into something that is very reliable. So here's an example. You can see as this gentleman moves across camera, it sort of transitions smoothly. And sometimes he's blocked in some views, but it's still stably tracked. And the plan is, once we get this tracking to work, we can sort of also recover the position of, your head or shoulder or knees in the physical space, and hopefully that will make it easier to do exercise recognition. And we have been sort of looking at what's available in these areas for a couple of months, and we think in trying to bring this system to work, we have seen some interesting research challenges. And in the rest of the talk, I will just highlight a few of them. So first, so we, in general, we want to develop a system that realizes a certain function, and we wanted to reach a certain performance level. So performance can, of course, be accuracy or latency or any combination of your favorite metrics. Okay, so this is kind of like the requirement, and then we decide how a system should look like. And the main parameters can be how many sensors, for example, how many cameras we want to deploy. And it can also be what kind of devices. So in the gym case, it can be not just camera, but different IR sensors, depth sensor, and so on. So that's one axis. And another is sort of how powerful do we want the individual devices to be? Do we want to run some constrained models on very close to the sensor, or do we want to do some powerful things in the cloud and so on? I guess another way to view it is how much compute you want to do on average for each individual data stream. And then there's this this nice green area where you can configure a system in this way, and you can reach your performance requirement. And it's possible to do research along either of the axes. You can try to do optimization on the vertical axis, and that's more sort of like trying to improve the performance of each individual device. You can do better algorithms, try to do model compression or pruning, or try to design better hardware. And it's also possible to work on, more on the horizontal axis. So that's more like saying, well, let's just accept that if we want something that runs in real time, there will be some performance loss, and even the best technology we have available right now is not going to be robust enough. But let's just try to make it up by deploying a lot of devices and try to do some research in how to fuse all these data streams together in a robust way. So in the demo you have seen, we were fusing multiple camera streams, and it's also possible to look into different sensors of different modality, and we also have a project with Valentin that's looking at exactly this. So that's topic number one. Number two is sort of also something we have started to look at. So let's say we want to put up, we have cameras and we have some very, some CPU or GPU at the edge that's running some models, and they will communicate with each other or with some backend wirelessly. The cameras may be powered by battery even. So then we have some actual power and communication requirement that we want to optimize. And in this case, it's also, you can look at, try to optimize each individual device to make it run more efficiently or communicate more efficiently. But it's also possible to look at the whole network of devices. So an example might be, let's say I have a high-performing model, but it's a little bit expensive to run, and I also have a sort of average-performing model that's very fast. And you can imagine it might be the case that you only need to run the high-performing model on some of these cameras some of the time. So then an interesting question would be how to design an algorithm or a policy so that all the devices can work together. So that's just one of the potential directions. And then, it's on a more practical level. Let's say you even have a system that works, and now you actually need to go out and install them. So I don't know how it's like in the UK, but in Sweden, if you want to get a certified electrician to draw all these wires and cables, that's also very expensive. And you also need to maintain a lot of devices. So not to summarize, I've listed some of these topics that sort of not really about optimizing individual devices, but to think of the system as a whole and see how how we can design algorithms to make the devices to collaborate with each other more efficiently. And I just want to mention that actually, recently there are also some new data sets with multiple cameras and with some overlapping field of view. And so it's actually, you have a lot of opportunity to try out new research ideas on.
Thank you, Sangxia.